Uh, Hi, I'm Sorelle. We've heard a bit today, and probably yesterday, though I couldn't join you all, about the potential dangers, I guess, of using machine learning to try to actually understand what's going on in the world. And though I would hesitate to call what I'm going to talk about today solutions, I guess what I would say is that I'm going to try and give you some techniques that can be used along with serious domain expertise to try to understand a little bit more about what these techniques are doing. And that motivation for my work comes out of some work that I've done with chemistry colleagues, Josh Fryer and Alex Norquist, on trying to take information from Alex Norquist's lab and model it using machine learning. And we started off by figuring out what the data was and trying to set up a classification problem, right? Trying to essentially narrow the scope of what we were looking at to something that was a little bit more tractable. So in this case, it was trying to predict whether a crystal would form. And of course, that requires both positive and negative examples. So we went back to old lab notebooks, gathered more data so that we would have failure data as well. And from that, we're able to model the system. And we were, in fact, able to model the system and set it up in a full loop so that we were then able to use the machine learning model to try to recommend new experiments that should be performed. Those were actually performed in the lab, right, to essentially validate that the model was good, but also to perform new interesting things in the lab. And then indeed, those were more successful than a sort of similar human-driven process. And originally, from my perspective as the computer scientist involved in the project, I thought, okay, great, well, we're done, that was successful. And my experimental chemist colleague pushed back on that and said, well, but what did we learn? Right, okay, so you have this machine learning model that seems to be doing better than humans. Are you really going to tell me that that's it? That you're not going to tell me anything interesting scientifically from that, which I thought was a very good point. Right. So the rest of my talk sort of picks up from there. How can you take something that is already a model, some model that you believe for whatever reason has value, right? Hopefully you've done already lots of statistical analyses to make sure that the data that you're looking at is valid, that the model is actually predicting something interesting, and so on. Suppose you have that type of model, then what can you do to try to understand what patterns it's finding, imagining that this might be a potentially complex model. So first I'll talk briefly about the technique that I took in that situation, and then I'll move on to talk about some other approaches. So one somewhat simple approach, right, which I think is simple in the sense of being beautiful, is to take the model that you have and take the data set that you have, and you've used that model to predict various outcomes on that data set, write down all of those outcomes, and then try to predict those outcomes, but try to predict those sort of new predicted labels using a model that is naturally more interpretable, right? So you might have been using previously something like a deep net or an SVM, which are hard for humans to wrap our head around. But there are models that you could use that are more understandable, right? But might not be as good at finding the patterns that they're going to generalize across in the first place. So these are things like decision trees, right? Now the caveat, obviously, if you're looking at this decision tree and the decision tree is modeling something that was originally a deep net or an SVM, in this case it was originally an SVM, is that you're not really looking at the same model, right? So you're sort of one step removed from the real thing you're trying to study, but at least it gives you something you can look at. And that's what we ended up doing in this situation, right? Now the problem is, in order to model something complex, you're going to end up with a really big decision tree. So this is actually only sort of one branch of the decision tree, right? My colleagues in chemistry were patient with me and spent a lot of time sort of carefully looking at the decision tree, trying to understand what it was saying, and ended up with the different colors of highlighted nodes are actually the formal hypotheses that they were able to derive from this and then go back and test in the lab, right? So I think that this is one possible route, right? And if you're really dedicated to a specific data set and willing to take the time to try to understand what's going on, it can be useful. But I think also, obviously, it's useful to have some techniques that don't require that much sort of intensive labor. And so mostly what I wanted to focus on today is thinking about feature influence on a model. How do you determine which features were most important, and how do you quantify that? And specifically, I'm interested in doing that for these black box models, right? For things like deep nets, but also in some cases for models that you only have access to run, right? So things that are maybe accessible only via an API. So what I'm going to assume here is that you have access to the model in the sense of being able to give it new data and see the outcomes on the new data. And the main question that we're going to try and understand and answer to is, does a specific feature have a large impact on the outcome of the model? And there's two different ways of thinking about what I mean when I say, does it have a large impact on the model? And I'm going to call those direct versus indirect influence. And I'm also, you'll notice highlighting here that, for those of you who like playing with code, the two specific techniques that I'm going to talk about are pretty easily downloadable and installable. So what is direct influence? Direct influence means that you can imagine that feature directly impacted the model's outcome. So if we had a decision tree, you could imagine that the name of that feature is actually written on one of those nodes in the decision tree, right? There's a decision point directly made by that feature. On the other hand, indirect influence are features that might be proxies for features that were used by the model, right? And what you want to be sure of, suppose that you have a whole bunch of features that are chemical properties, and you want to understand how the outcome was determined, right? We would never want to say, well, pH didn't actually have an impact on the outcome, right? Because probably some other property that's correlated with pH did have an impact on the outcome, right? And so indirect influence tries to incorporate those sort of proxy influences into our final calculation of the importance of something like pH. So just to give you a concrete example, that's just a little toy example so you can understand a little more of what I'm saying. Suppose that you have some data set, and it's a very simple data set. You have A and B, and they're direct proxies for each other, right? They might even just be exactly identical. And they're also direct proxies for the outcome, right? So specifically, we have this little decision tree up here, right? And so if A is bigger than 1, then we're going to say yes, and otherwise we're going to say no. And that's it. That's our whole model that we're going to audit. And we also have a random feature and a constant feature. If we looked at calculating the direct influence of each of these features based on this specific model, most of these techniques would find that A had a direct influence that was high. In this case, high is going to be 0.5 because what we're going to end up measuring is the drop in model accuracy. In other words, 0.5 takes it down to random. And then the other ones should have 0 influence on the model, right? Because B, random, and constant are never in any of those decision tree nodes. Only A appears in those. Right? On the other hand, if we're looking at indirect influence, the question is, does, say, B or one of its proxies have an influence on the outcome? And since A is directly in one of those nodes and A and B are proxies, they should end up having the same influence if we're thinking about indirect influence. Okay, so how are these things measured? So there's a couple of different methods for measuring direct influence. One of the most common is perturbation. And the idea here is that you take the feature and you randomly swap some feature values with other values for that feature in your data set. You send that modified data set back through your model, and you look at the drop in accuracy, right? And that amount of the drop in accuracy is the importance of that feature. There's a large caveat with this to the extent that there's a recent paper that just came out titled something like, "Please stop using feature permutation as a measure of importance." So the large caveat is that it doesn't handle correlated features well, right? Because if you had two features that always appear together, and now you randomly swap in a different one, you're going to randomly swap in one that the model has never seen appearing with that other one. And what you're then going to be measuring is actually just what the model is likely to do when it extrapolates to space where it's seen nothing, right? Which is not what you meant to measure. So that's the large caveat there. The benefit is it's sort of easy to understand what it's doing, right? But you always have to keep that caveat in mind. There's another technique that doesn't quite suffer from that caveat that relies on a game theoretic notion of shapely values. And the basic idea here is that you want to actually look at the average contribution of the feature if you look at all possible coalitions of features. And essentially what this allows you to do is understand sort of what the, I think about it as measuring the importance of that feature with respect to some baseline prevalence, right? So that features don't receive sort of outsized importance just because a particular phenomena is common, right? They only get the sort of extra marginal importance of that feature. And then finally, indirect influence, which is what I'm going to spend most of my time talking about, is does that feature have an indirect influence on the outcome? And the direct perturbation methods no longer work here, right? Because now if you were going to imagine that you were going to randomly scramble a column, well, you'd have to do something with the other columns that are correlated with it. And if you have something that's correlated with most of your data, right, you want to make sure that you're not in a situation where you're just throwing away all of your data, right? We want to somehow preserve the pieces of the signals of the other attributes that are not the thing you care about here, right? So how do you do that, right? Oh, and then once we've managed to sort of remove a feature from the data, we're going to do that same trick of sending our revised data back through the model and looking at that drop in accuracy. And we're going to call that the influence. Okay, so how can we remove this information from a data set without just removing all information from a data set? And the basic idea here is that the information content of a feature can be estimated by trying to predict it from the remaining features, right? So if you have some feature, say pH, and you have a whole bunch of other properties, the information content of pH, right, is essentially the amount to which you can use all of those other properties and accurately predict the pH. And it's an if and only if, right? So if you can't successfully predict that, then you have successfully removed that information. And what this looks like, what we end up doing to try to achieve this removal of this information, is that we look at the marginal distribution. So here we have two values of some feature that we're trying to remove, right? So this feature we're trying to remove takes values red and blue. And we're looking at this other feature that's continuous, and we're saying, okay, how do I try and remove the red and blue information from this, right? Now that's tricky to do because those two are separated, right? The marginals are separated for this other feature. And so what we're going to do actually is create that median distribution, that median black distribution, and we're going to move the red distribution and the blue distribution to that median distribution, right? So we're going to modify all of those data items so that they are still in the same order along the distribution of the data item that we care about, but they're now going to take on values that they didn't originally have, but that will make it so that you actually can't recreate the information about whether they were red and blue from that data, right? And in fact, right, it'll fail an F-test that tries to distinguish between those two distributions because we've purposefully pushed them together, right? Oh, looks like I have a slide mess up here. Oh, and we also have experimental evidence that, you know, if we perform this technique and we then try to recreate that information, we can't do that. There's an important caveat here, which is that we have only done this essentially along one dimension, right? So if you have some features that are correlated across a highly multidimensional space, right, this particular technique will not manage to fully remove that influence. There's sort of other techniques I'm in the process of developing that might manage to do that, right? But it's still very much, these methodologies, all very much an active area of research. Okay, so what happens if you apply this to some real data set? So with this same colleague, I'm now looking at a new data set focusing on perovskites. And we have a whole bunch of different chemical features that we're trying to understand the influence of the outcomes there. And that's essentially the x-axis, lots of features into our model. And on the top, you can see the direct influence of the features. And on the bottom, you can see the indirect influence of the features. And what you'll immediately notice is that there's a whole bunch of features that the model seems to not directly be using, but that do have a lot of indirect importance. Right? And this is useful to us in terms of understanding the chemical properties that we're looking at here, because what we can see is that these features are actually important to the outcome, right? They actually do have chemical meaning in this system. It just happens that the model is not directly using them, right? But in other words, my hope is that these techniques will keep us from making conclusions of the sort, oh, the model is doing a great job of predicting this and didn't use this chemical property at all, so therefore this chemical property is not important to the system, right? That would be an incorrect conclusion to draw. What we instead need to try to understand is that all of these properties, right, have varying amounts of importance. And so I guess what I would sort of close by saying is that my hope is that we can use this type of technique in combination with domain expertise to try to understand how features are important to a model, and hopefully also through that get at how they're important to the underlying system that we're trying to examine. Another few interesting points about these techniques is that indirect influence can actually be performed even for features that aren't in the model, right? And this is useful if you're trying to understand somebody else's fixed model, and you say, you know, they didn't actually take into account this set of features at all. I wonder if those are perhaps working through some proxy variables in their model, or whether they're actually missing that information, right? You can actually use an indirect influence audit to detect that. And finally, and this I sort of realized by talking to a colleague who does environmental oceanography, and she has dive data from dives that happened in different locations and at different depths. And she was finding that when she went to model outcomes on that data, essentially it was just predicting which dive it was, right? Because there was so much information that was correlated together about the dives, right, that it was sort of missing the things that she actually cared about. And this is still somewhat tentative because we haven't managed to sort of fully validate it experimentally yet, but I suspect that these techniques can also be used to purposefully ignore features like that, right? So part of this indirect influence audit takes the data and changes it so that you can't find this information. So if there's information that you know shouldn't be part of the model, but you don't have data that exists without that information, right? Then you can essentially remove that piece of data from the model, and that'll give you a new data set that you can then use to model that won't suffer from these, say, knowing which number dive it was on. With that, I'll close. Thank you.